Okay, Kayla, so let's move on with section 6-7. So for 6-7, we're going to deal with a lot of the same shapes that we've been talking about, but now what we're going to do is we're going to put it on the coordinate axes. So nothing new that we haven't learned already. The only new sort of topic is essentially dealing with all the different properties that we learned of quadrilaterals. So what I want to do is just do one example, and I'll show you how we're going to use the distance formula, the mid-segment formula, and maybe the slope of the line to try and determine what these shapes that we have on the coordinate axes is. So the first one I want to do, it's number 9 in section 6-7. Like I said, there's nothing new here. We just have to interpret this on the coordinate plane. So it tells us determine whether the parallelogram is a rhombus, a rectangle, square, or none, and then is asking you to explain. So for this, they have L is 1, 2, M is 3, 3, N is 5, 2, and finally P is 3, 1. So we're going to plot these points. I'm going to try to make a really accurate graph here so you can take a look at it. So actually it looks like everything's basically living in the first quadrant, so we don't even have to show too much on the other quadrant. So I'll just do this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5, 5. So I'll plot the first point, and that's going to be L, and that's at 1, 2. Right? 1, 2 there. 3, 3, that's going to be M as in man. Here it might help to 1, 2, 3, 4. Be a little easier to follow along here. So at 3, 3, that's here. That's M. N is 5, 2, so there. N is in Nancy. And then finally, P is 3, 1, which is there. Oops. So we have this shape here. So it's kind of looking like a bit of a kite, right? So it's going to be, well, since they didn't give us that option, actually, I'm looking at the directions again. It's either a rhombus, a rectangle, a square, or none. So, I mean, it looks like a kite, but there's only one way to tell whether or not these lines are going to be parallel, and I have to obviously find the slope of the line that connects these 2 points. So there's a couple of lines that we have here. Let's take a look at the slope of this line here that goes through L and P, and the slope of this line here that goes through M and N. So the slope, the equation for slope, remember, is y2 minus y1 all over x2 minus x1. So we'll do it for M and N, right? So for these two first, want to know the slope of that line. So the slope, I can't write it all out here, and it just doesn't fit. So I'm going to go ahead and just write it in. So just follow along for the slope between those 2 points that I highlighted, M and N. Y sub 2, just go 3 minus 2 all over 3 minus 5, right? So that's going to be 1 over 2, or minus a half. Now that's the slope of the line that connects the points M as in man and N as in Nancy. So the slope of this line here, I don't want to keep using M. I don't know why they chose M as a variable here. The slope for this line is minus a half. Now let's do it for L and P. Use maybe a different highlighter here. L and P. I'm going to do the same thing. M for slope. Let's go 2 minus 1 all over 1 minus 3. And this again is going to be minus a half. So it turns out they have the same slope. So this line also has a slope minus a half. So these two lines are parallel. That means these two sides are parallel, parallel, parallel. Now the distance L and P and M and N, we're going to have to determine that using the distance formula. So LP, right? We're going to use the distance formula. I'm kind of run out of space here. This is a pretty involved problem here. So let's go and recall the distance formula really quickly. So we have that the distance is going to be the difference in the x's, quantity squared, plus the difference in the y's, quantity squared. And then we have to take the square root of all that mess. Boom, right there. For L and P, I'm going to take the difference of the x's. That's going to be, let's go 1 minus 3, quantity squared, plus the difference in the y's. I did 1 minus 3. Let's go 2 minus 1, quantity squared. And then we have to take the square root of that. Now 1 minus 3 is a minus 2, and when you square it, you get a positive 4. 2 minus 1 is a 1, and when you square that, you get a 1. So you end up getting the square root of 1 and 4. So it's the square root of 5. So the distance from L to P is the square root of 5. Let's do the same thing for M and N. So M and N, we take the difference in the x's. Let's go 5 minus 3. Doesn't really matter what order you do it as long as you keep it the same. I like 5 minus 3 because I don't have to worry about negatives. And let's do 2 minus 3, quantity squared. So here we get 5 minus 3 is 2, quantity squared is going to be 4. 2 minus 3 is negative 1, quantity squared, you're going to get a 1. And that'll be the square root of 5. So it turns out that the distance LP and MN are one and the same. That's the square root of 5, and that's the square root of 5. So we're going to do the same thing. And I have a feeling it might actually be a rhombus. We just have to figure out that the opposite sides are parallel. So we're going to do the same exact thing, but we can actually save a little bit of time, and I'll show you how. We're going to do it with LM and PN. So the slope here looks like you went up 1 and then over from 1 all the way to 3. So up 1 over 2. From 1 to 3 is a distance of 2. And here, looks like you went up 1 from 1 to 2, and then over from 3 to 5. So up 1, 2. So they're definitely the same slope. From L to M, you went up 1 and then over 2, and then from P is in person, to N as in Nancy, you went up 1 and over 2 again. So they're definitely parallel because we have the same slopes. So now we have this. So the only thing left to check is that the distances are the same. So now using the distance formula, we can figure out what the distance from L to M is. I wish I had more space here. Let's go ahead and erase something here. Let's get rid of this. We already know what the slopes are. In fact, you could have done the same little exercise initially. It would have been a lot less work, but it's all right. Do it this way. So let's figure out what the distance L to M is, right? The distance formula tells us for LM, we take the difference in the x's. So let's go 3 minus 1, quantity squared, plus the difference in the y's, 3 minus 2, quantity squared, and then the square root of all that. This is 2 squared plus 1 squared. Again, we're getting the square root of 5. Right? And we can do it for, let's say, we already did, so this is the square root of 5, and this is the square root of 5. Let's do it for N and P. So same thing, N, P. The difference in the x's, we'll do 5 minus 3, quantity squared, plus the difference in the y's, 2 minus 1, quantity squared. And if you take a look at all that, and you clean it up, you're going to get the same thing, the square root of 5. So we've got square root of 5, square root of 5, and we have all the sides, they're parallel, right? We looked at the slopes. The only other thing I want to make sure is that these blue lines here are not perpendicular, because if they're perpendicular, then not only, this isn't necessarily a rhombus, it's actually a square, right? So we already know the slope for both of these lines, right? The green, we have a slope of -1/2 and we have a slope of 1/2. So they're not, we talked about perpendicular lines and they're not negative reciprocals of one another. So -1/2 and +1/2 are not negative reciprocals. So these lines are not perpendicular. So that's how you would actually determine whether the interior angles here are perpendicular, right? So when you plot the points, go ahead and just use rise over run. I think that might be easier than actually doing the slope equation or slope formula. It's going to be a lot of work. And you can see on my little drawing here that I did quite a bit of work, but basically just use the distance formula for each one of the segments and then find the slope. So just go up and over depending on what the slope is. And remember, for two lines to be parallel, the slopes have to be the same, and for two lines to be congruent, the slopes have to be negative reciprocals of one another. So a lot of this just builds on everything that we've learned. We know all these definitions. We know what it means for a quadrilateral to be a rhombus or a square and so forth. So now what you have to do is check. You have to check the same segments, check the distances to see if you're getting congruency on any one of these. So I'm not going to spend too much time on this section because it's a lot like the next section that we're going to do, and it's the last section in the semester, and it's going to be section 6.8. So we'll take a look at section 6.8. I don't believe we have any new theorems in the next couple sections that we have here. So we'll take a look at it here. And we'll do an example. Let's do number 7 on page 410. Like I said, no new theorems. We just have to apply what we've learned to what we call coordinate geometry. And it's called coordinate geometry because we're dealing specifically with the coordinates. So number 7 is, what are the coordinates of the vertices of each figure? S, T, O, and W. And it says a rectangle with base B and height H. Base B and height equal to H. Now they're doing it all symbolically, right? We just have to go in and just be specific. So that means that this is H, this is H, this is B, and this is B. So those are the distances. These are equal to one another, and these are equal to one another. That's the definition of a rectangle. Now, the coordinate here, it's on the y-axis, right? And this looks like it's on the origin. So that one's easy. That one's 0, 0. And the coordinate here for W, it looks like it's still on the x-axis. So any point on the x-axis has a y-coordinate of 0. And you went B units because the base is B, so it's B comma 0, right? Now back over here to the point S, we're still at 0 for x because we're on the y-axis, but we've gone up h units, so this becomes 0 comma h. And for t, I've gone over b units and up h units, so we get the following coordinates. So really not too bad. You just have to, draw it out and you can start putting the values in. So I didn't give you too many of these for homework. I gave you just a couple. This is a lot actually easier, I think, than the previous section we just did. Nothing new here, so you have to kind of work through some of these to see if you remember the distance formula, midpoint formula, but you should be good. We'll kind of regroup once I get back, but this is all of first semester, so we covered all of chapter 6. We're going to skip 6.9 because we did one additional section that we don't typically do, and that was 6.6 with the kites and with the trapezoids. So we'll regroup for second semester. We'll start chapter 7. We're skipping, I believe we skipped chapter 5. So we're going to start chapter 7 and we're going to discuss similarity.